Okay. Okay, so thank you, Christoph. Okay, so thank you, Christoph, for your introduction, and good morning, everybody. I hope you hear me well. Do I need to speak louder, or it's fine, right? Okay. So I will start by saying a few words how the world has changed according to my point of view. So in the good old orderly times, the emphasis is in orderly. The old times were ordered. UK or the Commonwealth had, or still has, a queen, but she was happy at that time. Not Trump, not Johnson. The world was kind of ordered. And so was it in computing. So we have order, we have list of instructions. The memory was organized basically, or is still organized basically in arrays. We have state, and then programs just run through the sequence of instructions, and each instruction communicate with the next one via reading or changing shared state. And with time, things became a bit bigger. We had much more data, but then we had this nice theory, relational algebra that we invented, and then we implemented it into compilers, SQL compilers. The world still became a little bit bigger, but still was ordered. And then, of course, multi-threading brought a bit of disorder. We got races, but nevertheless, still were under control thanks to this guy that invented a new theory, the theory of serializability, and thanks to clever engineering, we were able to give developers this transparent illusion of order despite races. So there was some disorder across transactions, but there was the illusion of order within transactions. We still had state, but we added these notions of isolation for memory and atomicity for mutation in time. So it was easy with this new theory and the compilers that came with it, or the engineering that came with it, to ensure application correctness. The infrastructure became a little bit trickier to scale, but still this was under the control of the compiler developers, or the that brought the theory into tooling. But today, the new normal is a bit much more disordered, much more complex and unreliable out there. And so is it in computing. So what do I mean? There are several characteristics of the new normal in computing. One of those being what I have called outside-in interactive data flows. So we were used to have the program counter have the control over the execution. It would run, as I said, through the instructions and then get or change the data. Now the control is outside. Events and data arrive in applications in our new data economy. We have Internet of Things and Internet of Things platforms. Everything is connected. We have collaborative software for businesses or just for ourselves. We keep interacting with each other over software platforms. So basically, data arrives, and this arrival of data, the data flows, drive the computation and not the program counter anymore. Of course, in any talk, we need to mention the big data. So the data has become much, much bigger, whatever definition of big data you have. The next thing is the globalization of computing. So we have computations happening everywhere in this range across devices, in the middle part, in the near end, to the far end, to the cloud. Our applications on the devices are connected to the cloud, have stored our hosted services on the cloud. The big systems on the cloud are themselves massively distributed. And what is important is not only that we have this big global computer now, all these devices and desktops and clouds be connected to each other, but I think there is this trend also to have decentralized applications. So to have computations happening on the edge of our globalized computer for several reasons. Here I give just two examples for illustration. So this is taken from the web page of page of Qualcomm, saying we bring intelligence on your device. So AI happening on devices, happening on the edge, highly decentralized. Another trend is this trend of personal data stores. Instead of having data centralized at Facebook's and Google's of this world, we have our personal data storage. The reasons for, and we have computations happening on our devices where we have our personal data store. And the reason for these decentralizations, I mean, there are several reasons. Privacy, obviously, on that corner, but also reliability, low latency, and also efficient usage of our network resources. Okay, so change in the way we interact, in the way the computations are driven, global computing, decentralized computations. And I claim that this new normal, the new normal out there is challenging the traditions. I hope you all remember how traditional protocols were broken during the last visit of President Trump in the UK. But also the new normal in computing is challenging our traditions of programming. What do I mean by this? I mean three things. First, I said, data flows determine execution order, not control statements. Of course, we have had exceptions all our life, all way, but they were exceptions. They were interrupts. We had interrupts, but they made the exception. Now, interrupts, control from outside, from data, is the normal. And our systems are used to have the control statements have the control over the execution. Now, with this global distributed world, some of our ways to establish order, like transactions, for example, or synchronization protocols, are being challenged, are being turned into forbidden fruits in terms of being too expensive, maybe, in the global scale. And the third thing is that while we'll have this big data, having big data means that we cannot put our attention and structure our computations around individual data. What is interesting and important are correlations of data. And we need to organize our computations around data correlations and event correlations. But still, I claim, and unfortunately, probably I will not be able to go deeper in this part of the talk. I claim that we lack, while data correlation is such a basic abstraction, we need simple theories for programmable data correlations. Let's see how far we go, whether I go deeper in this part. I will start with the first two parts, and I was, I think, too fast. Oh. Okay, so I said that the new normal of computing is challenging our traditions in programming, and that's why I'm claiming during the talk that we are in need for new, affordable illusions, for abstractions that create new, affordable illusions. And I really like this cartoon. I don't know if anyone in the room knows where the cartoon. Okay, yeah, people like me with a little bit of white hair remember, this is from Grady Booth's book on OO design. This is probably one of, well, first books that I had in my hand when I was a PhD student, and I really loved the book for the cartoons it had, and especially this cartoon. I've been using it all my career. It basically says that the task of software development teams is to engineer the illusion of simplicity for software users, for this old lady there. But I'm saying that the task of a PL researcher, our task is to engineer the illusion of simplicity for the developers themselves, so that we get a little bit of handle on this mess inside the box. Okay, first part, what does it mean to create illusions for data flows? So as I said, we have this inversed control, and we do have maxims, we do have design patterns, if you want, to handle with the inversion of control. Everybody knows the observer pattern. So we have this mismatching between instruction order and data flow orders, and we have this answer to address this mismatch, which is the observer pattern or callbacks, if you want, and they are nowadays everywhere. So when some interaction happens, an event is triggered, this event triggers a callback to be executed, and callbacks interact with each other while changing state. But we also all know, and you just need to type callback in Google and you get the completion callback hell, that callback-based designs tend to become hell. Because I claim maxims and design patterns are no replacement in the long term to proper abstractions. What does it mean? Why we end up with so-called callback hell? Well, we need to actually implement all those callback interfaces, to register them, to bring together observers and subscribers. All this creates boilerplate code, but that's not the worst part of the story. I say it's rather the very contrived, very complex control flow that occurs during runtime, because all those callbacks, as I say, they interact with each other via broadly scoped state variables. And this is very old. I mean, 2006, there was a report by Adobe saying that 1/3 of their desktop application code is devoted to event handling, and half of the bugs during a product cycle exist exactly in this code. To make it a bit more tangible what it means, I'll give you an example. So assume I have this piece of code, and I'm asking you, the question is, what does it do? Let's go together through it and see what does it do. So this is written in a version of Scala, and it has support in this version for explicit support for events. So I have declared a couple of events, and some of them are defined by composing other events, like new day and new week. And down there, this tick, new day, new week, are callbacks. I attach callbacks to the events. What happens if I try to execute this program on my slide? Let's suppose a tick is an external event. It happens. When it happens, the callback associated with it will be executed, which in the body of the callback changes the hour, this variable, globally scoped variable. When the hour changes, it might turn the predicate that defines another event, this new day, to be triggered. Once it is triggered, the associated callback will be executed, which changes another variable. The change of this other variable may cause other events to trigger and other callbacks to execute. So a pretty contrived, pretty complex control flow, which is hard to understand, and hence the code is error prone, because changing this code, means understanding what happened, and it's a very small piece of code. If you have big systems, you can extrapolate the problem. Okay, so that's why I think we need programming abstractions that embrace order imposed by data flows so that we can enable data-driven computations. That's what I meant in my title with let it flow. Because the logic I wanted to express is as simple as expressing the dependency between a tick happening every hour, definition of an hour, definition of a day, definition of a week. And this is as simple as expressing those constraints here if I only had the right programming abstractions, which I do have in languages that call themselves reactive programming languages or functional reactive programming languages. And in my team, we have been developing one such language called Rescala. The name says it's basically a reactive version of Scala, a reactive extension of Scala. It's not a new language, really, because it's implemented as a set of libraries embedded into Scala. What's the key abstractions? Really, there are only two key abstractions. Signals is one of the key abstractions. So there are variables, sources, where input and new data come into the systems. And then there are signals that are defined, computations defined, depending on other computations, but they are self-evaluating. So every time the inputs change, the computations trigger reevaluation and reevaluate themselves, bring themselves, their state up to date with the inputs. That's why on the slide, this Excel spreadsheet, because those computations are resemble spreadsheets in the sense that I can define formulas in a cell depending on other cells, and once the input cells change, the formula becomes, the value of the formula cell is brought automatically by the system up to date. Same thing here. So changes in the system are propagated automatically through dependent computations without the developer having to do this manually or imperatively. So in Rescala, I mean, this is kind of pseudocode, but this is how our functionality will look like. So I define a variable tick. It is used in those signal computations, and every time tick has a new value, hour, day, and week will recompute automatically, will be automatically brought up to date. The inspiration came from the functional reactive programming languages, and Flapjacks, as far as I can tell, was one of the first works that brought these abstractions to the OO world, or to the, at that time, to web programming. So in order to understand, let's go through an example to see what's happening, what Dataflow programming in Rescala means. This program is a simple one. We have a list. We have a variable, a value index. We get the length of the list, and then there is this if statement here that basically makes sure that we don't access the list out of bounds. So if the index is smaller than length, then we get the element of the list at index. Otherwise, we just return some dummy value, and then whatever the selection is, either the dummy value or the list element at index, we just print this element. So this is kind of a piece of program in not yet reactive mode. To make it reactive, I will make it reactive. So let's assume now we have index equal 1, and we go through the statements, which I said, and this will print B. Now I turn it into a reactive version by making list and the index variables, so sources of change, and the other computations turning them into signals. Which means that if down here I change the index or set it to 2, these automatically will make print to show the value C. Because the data changes flow through the computations, like once the index is changed, it will trigger, it will signal the change to all dependent computations, in this case value, and also print, which then get their value up to date. How this is supported behind the scenes, the program is, if you want, translated, mapped to a Dataflow graph. You see here the inputs down there as triangles, list, and index. Those are the sources of the values, and the signals are represented as circles. So when I change the index to 2, the change is propagated to the selection, which becomes C, and print becomes C again. Okay, an important feature is this synchronous update semantics. What does it mean? If I start with the consistent state of the propagation graph and I propagate one change, this propagation from the source to the end nodes is perceived as an instant, is an atomic change. That means intermediate changes on the graph are not observable to the outside world. So every instant or every update, which happens as an instant, moves the graph to a consistent resting state. And this is achieved through this property called glitch freedom of the change propagation. And to illustrate it, let's go again through an update. Now let's assume that we remove an element from the list. We remove B. Now this change will be propagated through the graph. Again, so the list is changed to have B removed. Length changes need to change to 2, but assume that we have a diamond here, and let's assume that the change arrives to selection before length has been changed, and selections reevaluate at that point, which will cause an out of bound because the length was not updated. The glitch freedom property ensures that this cannot happen. So cell will only reevaluate at the moment where all its inputs have reevaluated, are in a consistent state. So basically, we'll have to wait length, and only then cell will reevaluate. And in this moment, since we indeed index is smaller than length, the answer will be none, would be this dummy value. That means the graph itself has changed dynamically. The dynamic changes in the graph can happen because of these things like conditional statements. There can be higher order reactives, so reactives that are contained in other reactives that cause the graph to change dynamically. But this is fine, so we do support dynamic dependency graphs and this glitch freedom property. How is this glitch freedom ensured? Is basically every node decides by itself in a autonomous way whether it can reevaluate or not. And you can think, conceptually about this like this. Assume that we have a change starting here, and we are now at this node needs to decide whether to reevaluate or not. The node just needs to know its neighbors and ask whether they have reevaluated or not. In this case, reevaluation is shown as circles that are filled. So we are looking at this updating the orange change. So in this case, we need to know whether to fill this orange circle. And this is unfortunate with them. Basically, it will ask the neighbors, and if they have evaluated, it doesn't need to wait, or if a neighbor node is not affected by the change, given that we have the dependency graph, we know which nodes are affected by a change in the source, so the node can decide what to do. Overall, to give now a high-level view, the Rescala runtime looks like this. So we have this propagation graph in here. We kind of think of the world as being split in an imperative and a reactive or functional world, if you want. The imperative world causes changes which are intercepted, so to say, are given to the propagation algorithm, which causes reevaluations in the graph to happen. And each node in the graph is associated with a user-defined computation, the signal computations, which are invoked in the order imposed by the dependency graph. And then the execution of the individual user computations can cause also side effects to the external imperative world. I talked about signals, but in Rescala we also support events. You saw actually in the example slide that there were this declaration of events, and there are expressions to compose events into more higher level events. And we do also consider events and signals as being types, if you want, concepts of reactives. We think of them as both reactives, and they are interchangeable. We have operations that, given an event, turns the event into a signal, which is a time-changing value with all the values that the event exposes, or the other way around. We can, having a signal, we can turn this signal into an event by just triggering an event every time the single value changes. And this also helps in reducing the need for callbacks, because assume I want to have given an event with all mouse clicks and a signal, a time-changing value with all the positions of the mouse. I want to have to define a new single last click, which also only contains the values of position when the mouse is clicked. We do have this operation snapshot, which composes the two. So it says create last click up there from position every time there is a click event. If I didn't have such composition operators, I would have to go back and use callbacks and shared values, which will again reintroduce those complex control flows. Okay, so far so good. What I have talked so far is basically a change in a paradigm shift in terms of going from a world where we basically track dependencies between computations in an imperative way, in a programmatic way, to a world where we have automated flows of signals and events through dependent computations. What I didn't mention so far is that signals are so far primitive values. So what about complex data types like collections? We are in the signal world a little bit in a pure functional world, in the sense that when a collection changes, when an element in a collection changes, this is perceived as a change of the whole collection, and it's propagated as such. That means computations that depend on those computations will have to be redone on the new value of the whole collection. Of course, one can go and do workarounds, use events to kind of notify about fine-grained changes of individual elements in the collections. But here we are back to the callback world, and we wanted to avoid this in the first place. That's why Rescala also supports incremental collections or reactive collections and reactive computations on collections, if you want, which I basically will go very fast through this. It's just for you to note that they are there. So here, let's assume we have these tables, airport and flight, and we define a query, select from where, and then we change the table flight down in the slide. And the idea is that this change will be propagated through the operator graph of this query. We basically define an incremental relational algebra, relational operators that notify each other in the dependency graph. Good with this, because okay, so far. So I give you the basics of Rescala, and I started with the claim that we need new programming abstractions to create new illusions in a world that is driven by data. Now, how do we know that we achieve this goal? And the hypothesis during all my talk is that this declarative style with signals and events and event propagation and signal propagation improves application design quality. It gives us more composable abstractions because it avoids callbacks, is less error prone, and easier. It supports easier program comprehension. But we don't really know, right? I mean, the paper on flapjacks at UPSLA 2009, exactly 10 years ago, you can find some sayings there that obviously the flapjack code may not appear any easier to a first-time reader, so we wanted really to know. We did some, initial empirical evaluations. Two empirical studies, if you want. One was, we asked the question, do composable event and signal abstractions really improve application design? What do we mean by improve application design? Basically, reduce the number of callbacks. And what we did was to have several case studies be implemented in two versions, in OO plus callbacks, and with events and signals, and found out indeed that we have significantly more composable abstractions. The other study was a user study. What we did was to ask the question, does RP abstractions really improve program comprehension? And what we did was to have 10 applications written in Java plus observers or in Rescala, and we had 40 students divided in two groups, and they were asked questions about those applications, and we measured kind of how correct were the answers, how fast were they with the answers, and we found out that indeed the reactive programming group gave significantly more correct answers than the OO group. It was significantly faster in half of the task, and not slower, not significantly slower in the other half. These are pretty good results, especially if you think that the students that were involved in the study had Java from the first semester and learned about Rescala only in 2 weeks. Of course, those are very preliminary studies, and we need to scale them, but there is an indication that indeed this is true, that signals and events and data flow abstractions help with design quality. I want to summarize this part of the talk, so just give you an overview of the papers. So the first ideas about Rescala appeared at Modularity 14. Then these empirical studies that I mentioned appeared at FSC 2014, were presented at a paper at FSC 2014, and then extended in a journal version for TSC 2015. The paper on the incremental collections appeared already at UPSLA 2014, and there is a follow-up work on it based on these incremental collections or reactive collections. We extended them to have language-integrated, privacy-aware distributed queries, and this is an upcoming talk at UPSLA, and on Thursday, Guido will be able to talk, and he is standing there, I see. Okay, but so far there were not much disorder in terms of, for example, races due to multi-threading. And the question is, can we keep the order, this synchronous updates of reactive programming can we keep the semantics in a setting where we have multi-threading? And the answer is yes, we can. We have transactional updates, and they are even better than the original transactions, and I will come to say what that means. Okay, so if I have parallel updates happening, then I might, even if each of them is synchronous, have this glitch-free property. When they execute in parallel, like here, the orange and the green, they can kind of conflict at nodes in the graph, do, for example, updates on the same node, and then again we will get here to inconsistent values being observed during the updates. So what do? The idea was simple, to say, why don't we look at one update as being one transaction, and then ensure serializability of those transactions in the sense of serializability as we know it from the database transactions. So they happen in parallel, the updates, but they occur to happen one after the other. They are serialized. How do we do this? We basically wrap the propagation algorithm, if you want, into a thread-safe wrapper, into a wrapper that ensures that the propagation algorithm itself is thread-safe, which means that the application doesn't need to change in any way. That's what we call syntactic transparency. So we have thread safety in a syntactic transparently way. We take an existing Rescala application that was not designed with multi-threading in mind. We can run it on a multi-threaded environment with correctness guarantees that the application had in a local setting, not a non-parallel setting, not concurrent setting. How do we do this? Basically, the transactions are not defined in terms of application level read and write. They are defined in terms of operation on the dependency graph. That's what makes it possible. Basically, we view all operations on the dependency graph, like reading a reactive, this is this now, or firing new, entering new values into the graph as transactions. Also, reevaluating a signal, performing an update, performing a set of reevaluations due to a change in the source is considered internally as a transaction. At runtime, we use multi-version concurrency control mechanisms, well-known mechanisms from the database community. What does it mean? In abstract terms, it means that every update keeps its own version of the value of reactives in each node in the graph. So we see here the state of the graph at a certain point before starting parallel transactions. The blue versions are the current state of the values of the reactive nodes. Now let's assume we start 2 updates in parallel, the orange and the green one. And the good news, what this declarativeness of reactive programming gives us is that each transaction before it starts knows the nodes that are affected by the transaction. It's basically the transitive closure, starting with the input node that is affected and going through the graph through all the affected nodes. So both transactions put empty versions, kind of claims, I will change this node without actually changing this node, the node itself. So it's just putting claims, holes, placeholders that there will be a computation by the respective transaction here. So in this state, both orange and green have propagated their placeholders until to the node cell. And at this point, we see that we have a node which is affected by both the orange and the green transactions. Here we need to establish an order. The first time they get together into a node, they establish an order, and orange says, okay, I go first. If for some reason now green arrives earlier at the node print than orange, the propagation will notice that now the order doesn't fit the order that was already established, orange before green, so we'll change the order of those placeholders. They are placeholders. There is no computation has happened so far, so they can be changed arbitrarily. And now that they have placed their placeholders, their claims to evaluate nodes, they can start executing. And the structure of the graph will determine what computation can happen in order to keep the consistency property. So at this point of the state, orange cannot execute, cannot reevaluate cell because it's still missing the reevaluation of len. Green cannot evaluate cell because it is ordered after orange, and since the placeholder of orange on that node is not filled yet, it has to wait. So the only possible execution, the only possible reevaluation is orange reevaluates len. And once this has happened, let's assume now that during the execution, during the evaluation of len through orange, we have this dynamic change of the dependency graph because we realize len is now smaller, or index is smaller than len, so we had this if then else statement. The result, the value of cell is now this none or dummy value. So we change the graph, and then let's assume at this point a third transaction starts, this pink. But since we know everything happened here, we know up to this point, orange has not executed yet, and green has not executed yet. So we can add new placeholders. We can correct the graph as if pink was there from the very beginning when the transactions put their placeholders. So now that we have all the placeholders in place and in the right order, the transactions can complete their execution and get to the final results on each node. So the green reevaluation is the final result here, the orange are the final result here, and the pink reevaluations are the final results for cell and print. And what is important to notice is there are no, deadlocks cannot happen, and hence there is no need for rollbacks. That's what I meant when I said we have transactional semantics with even better, stronger properties than what we know from database transactions. So we have serializability, but abort-free, which brings us to semantic transparency. What I mean is the following. I said I can take a Rescala program, which was not written with multi-threading in mind, run it on a multi-threaded propagation algorithm without changing it syntactically, and I will see no semantic change difference. If I had aborts, I would see semantic differences between the two versions. I don't see them here due to this abort-free property. And in order to have the abort-free property, we made use of these declarative abstractions that RP gives us. That's the point I want to make, that the declarativeness of the programming abstractions, moving data change management away from the program to the runtime, gives the runtime a lot of power to ensure that transactions updates can run concurrently in an abort-free way. To summarize, so thanks to the explicit data dependencies, they determine the reevaluation schedule ahead of executing reevaluation. This avoids the deadlocks and gives us deadlock and abort-free thread-safe propagation. Due to the glitch freedom property, we have a topological order in which the updates are propagated, and this ensures deadlock abort-free serializability even when the dependency graph changes dynamically during the runtime. Due to this one semantics, when a node is reevaluated, we are sure that its value will not change during the same instant anymore. This enables pipelining. So the updates can execute not only concurrently, they can execute in a pipelined way. So once a transaction is finished, has finished reevaluation in one node, the next one can continue on that node. So there is a fine-grained concurrency happening here. And the last thing is, since we encapsulate application state in the reactive abstractions, this enables us to have plug-in thread safety transparently into applications. This is this synthetic transparency. So all the 3 boxes with color, these contribute to the semantic transparency, and we have also the synthetic transparency. I will go fast through this slide. Of course, the question is that naturally raises, what do we have to pay in terms of performance, or do we scale actually with multi-threading? We didn't implement this multi-threaded propagation to gain efficiency in the first place. It's not about ensuring, supporting parallelism. It was about correctness in the first place, but still, having multi-threading, we need to scale. And basically, our measurements, without me going into details about our methodology, we basically took different topologies for the graphs, and then measured the throughput in terms of how fast updates can go through the graph with the increased number of threads. And you see here, blue is our algorithm. Green, we compared against a version of Rescala based on a software transaction memory, which we store all the states, so to say, in a transaction memory, and the version with a global lock. And of course, it's clear global lock doesn't scale. When we have a global lock, the system doesn't scale with the number of threads. But you see here that we can scale pretty well, even better than the software transaction memory, which is an optimistic concurrency control, in the case where this one scales. But you see here that for certain topologies, the STM doesn't scale at all. Okay, so to summarize this part, we get concurrency control, consistency in a multi-threaded environment, out of the box, means synthetically and semantically transparent and with good performance. This part was presented last year at UPSLA, the thread-safe reactive programming part. And I want now to move to the second part, the globalized computing world. Now we have transactions. The question is, do they scale? Does consistency, can we afford consistency in a globalized computing world? Of course, in such a globalized computing world, we have a lot of disorder. Disorder is the norm. State is broken. We have partitions. We have failures of different nodes in this globalized computing. And we have, on the other hand, the CAP theorem that tells us traditional answers providing memory consistency guarantees in order to reduce the complexity for the developers, can be or is in the perfect version impossible. So you cannot have both, 3 of them: consistency, availability, and partition tolerance. What do we do? And partition is a given here. As you see, state is broken, partition of state can happen, failures can happen in the nodes. The answer to this, the CAP theorem, which was formulated in 2010, was the emergence of all those NoSQL systems. And again, we resorted to using maxims and design patterns, commutative methods, inverse method, compensation. So if you are not able to complete your transaction on Amazon, so what? They will give you a compensation, a very simple example. So these methods are make it easy to scale the infrastructure, but it's tricky to ensure application correctness. The thing is, we don't probably need to drop consistency in an ad hoc way, just because we know it's impossible to establish perfect consistency in a world with partitions, while we want to have availability. First of all, there are ways to handling partitions and recovering from them. So Eric Breuer was the guy that formulated the CAP theorem in 2010, and he himself came to revisit his statements in 2012. You see, this is a citation from a paper that he wrote at IEEE Computer, where he said this was a good thing with the CAP theorem because it kind of warned us out there we cannot have the perfect consistency, but this shouldn't mean that we cannot have some form of consistency. We should drop it all completely. Because he says there is an incredible range of flexibility for handling partitions and recovering from them. So our goal, he says, should be to maximize combinations of consistency and availability. And I am claiming here that the reactive abstractions give us a very good way to do so, a very good means to do so. Let me explain what I mean. There is a whole theory out there, or still being developed, trying to answer this question in a systematic way. Is there a family of problems? And what is this family of problems that can be consistently computed in a distributed fashion without coordination? The problem is coordination. When we need coordination, and global coordination is expensive. But are there meaningful computations that can be computed without coordination? And it turns out there is a whole class of important such computations. There is a new theorem called CALM, formulated by a colleague of Eric Breuer at Berkeley, Joe Hellerstein, I guess, which formulates prerequisites or properties that computation have to have in order to ensure distributed consistency in an easy way, in an efficient way, without coordination. And we have all this work on conflict-free replicated data types, which also plays an important role here. This means you can replicate data and merge different versions of the replicated data without coordination, without the need for coordination, because they can merge in a conflict-free way. To illustrate the point, the CALM theorem says that in order for the computations to be easy to ensure, to be consistent, to be executed in a consistent way in a distributed world, in an efficient way, they have to be monotonic. They have to be, if you want, disorder tolerant. And to give you an example, here are two small, very simple computations. The first one basically gets a stream of inputs, and every time a new input of increasing numbers, I mean a new input in this stream of increasing numbers come, it changes the value next. So you would expect at the end, next would be the maximum number in the stream of increasing numbers. Another way to express this is to compute the max of the existing value and the new one arriving. This one is order insensitive. No matter in which order the numbers arrive, because you have unreliable network, the numbers can arrive in a disordered way, or you can, here the example is 5 comes twice, and it comes at the end. The computation on the left is non-deterministic, is order sensitive. Since 5 comes again at the end, the result will be 5 and not the maximum number, 92, in this stream of numbers, while max is disorder tolerant. When it comes to the conflict-free replicated data types, basically those are data types whose state can be expressed as a lattice. And they have a merge operator on this lattice. That means the states of replicated versions of the data type can be merged automatically in a conflict-free way. The most, an obvious example of such a conflict-free replicated data type is a set with the union operator as the merge. But there are a lot more out there that have been studied. And in the meantime, there are CRDT or conflict-free replicated data types libraries and even data stores, databases out there. The question is, how can we get those composable? And I think this is where reactive abstractions come to place. And that's why I claim we should bring them to the distributed world. There is a good reason to bring them to the distributed world anyway, because the distributed world, distributed applications are full of callbacks. And we started with the desire to avoid callbacks in application code. But what comes on top of this is that they also, as I will show in the next few slides, they offer affordable, or they make it possible for us to enable affordable correctness guarantees. Because I say they fit very well with this idea of monotonic computations and with CRDTs. Okay, if we bring reactives to the distributed world, that means our distributed data, our data flow graph gets distributed. So there are connections, edges in this graph that cross remote, cross network nodes. And when propagations happen in such a graph, they can conflict, right? So we have, again, the orange and the green propagations. They happen in this node and in this node. They share this node here, but they happened in the individual nodes here independent of each other. The question is, how can we merge the values when they come together? Basically, you can think very abstractly about how reactives and CRDTs come together, as I've stated in the slide. You could think of a reactive as a sequence of inputs, of input values, plus a fold operator that applies the user computation on the input sequence. When I replicate now a reactive, I basically replicate the input sequence, which can be easily represented as a CRDT and can be merged without the need for coordination. And then I run the fold on each node individually, on each remote node individually, on each replica individually. This is, of course, a conceptual view to tell you why I am claiming that the propagation algorithm is a monotonic computation, or can be implemented as a monotonic computation, and hence we can ensure eventual consistency out of the box again. So the nodes, the state can be partitioned, can get partitioned, the nodes can fail in the distributed graph, but when a connection is reestablished, the state can be brought into a consistent state automatically. And that's basically what this nice animation is supposed to illustrate now. We have these 3 reactives in 3 different remote nodes. There is one reactive replicated in 3 nodes. All communication in the distributed graphs happen through the replicated reactives. There is no message passing or whatsoever happening. And once those nodes change in individual nodes, and once we get a connection between the nodes, they can kind of merge their individual states in an automatic way. And we basically prove that this gives you end-to-end eventual consistency. State can change individual nodes independent of each other, but then get merged as soon as we have connections. And what is more, in Rescala, we also have support for not only for connections failing, but also for nodes failing. All we need is some persistent state in the individual nodes, and we can basically periodically save the state of the reactive graph in a minimal way. Again, thanks to RP properties, we ensure that we need only to store the inputs and the folds. Everything else is derived from input values in a functional way and can be recomputed. So we can make even trade-offs between how much state we store for recovery and how much state we recompute after a crash. Okay, so assuming some durable local storage and eventual consistency data types, which we use in the propagation algorithm to implement the propagation algorithm, we ensure full application durability and eventual consistent application state. There is proof that this is true, and this will be presented, the content fault-tolerant programming model for distributed interactive applications will be presented on Thursday at this conference. Okay, I think I need to come to an end, and just one statement concerning consistency. We can even combine strong and eventual consistency. We can have strong consistency within one node using our transactional model, but then eventual consistency across nodes. And I think I will skip some slides to come. Okay, I already stated that I will probably not have time to do this part, and it turns out I will not. Only to give you an intuition, we do have a lot of technology out there for correlating events and correlating data. It's not that we don't. All this zoo of technologies that are presented in the slide are available out there, starting with support frameworks for big data programming, for stream processing, complex event processing, reactive programming, concurrent programming languages. All of them do some or provide some means to do correlations. But what if it's so much different semantics, and I have no idea. That's why I said we don't have a simple theory of correlations, a unified theory of what it means to do event correlations. I have no idea when I need some kind of correlation semantics, where to get it from, which of these technologies to use as a programmer, and with which guarantees, with which semantics. What we need, I think, is a unification. And to give you an intuition, I just borrowed this analogy by Stoica, who says, we started with this, at the beginning there was the mobile communication technology. Since this was so great, we developed a lot of specialized devices on top of this technology. And at the end, thanks smartphones, we were able to unify these different silos into one platform and have them become composable. In this state, they are not composable. Now I can take a picture and send it on my tweet with the picture on my Twitter account. So basically, we need something similar for correlation semantics, and we have started working on it. There's been a paper last year at ICFP. It's still work in progress. Okay, at this point, I really want to finish by thanking also all my collaborators and students and PhD students that have been involved, and postdoctoral fellows and colleagues that have been involved in the big Rescala project. You see some of the names on the slide. Financially, the project was supported by an ERC advanced grant, which is finished by now, and you can find more documentation on the Rescala language and download it and play around and case studies from the Rescala page. With this, I would like to thank you for your attention and be very happy to take questions. Yes.
Thanks for a very inspiring and interesting talk. So I'm wondering, could you comment on what it is like to program error handling in reactive applications? I mean, I don't mean if the the algorithms are running, everything goes fine, but I mean, I might have parts of myself that failed for some reason, or that are dependent on things that fail, or maybe a computer crashes and just never comes up again, or I mean, things like that.
Yeah. Oh, I didn't want to do this. Okay, I will not go through the slide. We do have support for exceptions. The thing is also the way you handle exceptions have to change. You cannot handle exceptions in the old way of going back in the control flow stack, because the control flow is now orchestrated in a different way. So basically what we do in Rescala, we propagate exceptions just like we propagate values. And reactives have the possibility, let me see whether I have this slide, to basically react, this is the slide. So it's the same example, but I just access the list at the index without asking whether the index is within bounds or not. So here, an out-of-bound exception can happen. And then I have cell now, the reactive, saying recover, does kind of exception handling. It says, I want to handle the exception if it happens. If in the reactives graph there is no reactive that wants to recover certain exceptions, they will be propagated all the way through to the observers in the outside world. And the reactives in between do not need to care. So there is exception handling. It has to be specifically redesigned for this reactive world.
Hi. There was a lot in that talk, but on the first part where you talked about the data flow graphs, I was thinking a lot of similarity with the semantics of activity models in UML, something I've worked in. And I'm wondering if you looked at any of the similarities and differences there.
I haven't, to give a short answer. But I think, there are, even if, let's assume you are right, there is a lot of similarity. This is, I think, they fit well together because this is a programming technology and the other one is a modeling technology, so they can.
When you add the executable semantics, it becomes almost a programming technology.
Right. The UML activity.
The higher level signal processing in the UML semantics is different and much more message passing oriented. But inside an activity, there's a lot of similar data flow orientation. If you don't add explicit control flows of propagating things, potentially multiple tokens through, depending on events that are arriving. So there seem to be some similarity, including concept in UML of run completion, which is, I think, has some similarity to your transactional update that will go through more through eventful than through your sort of internal frame suite.
Mm-hmm. Okay, I have to look at it, but what about support for distribution?
You know, it's interesting. One of the intents was that the intent of the semantics is that you don't distribute necessarily an individual activity, but the activity is associated with a distributable object. And the objects communicate through message passing.
Message passing, okay.
But there's nothing to prevent distribution.
Right, I mean.
Within there, but that wasn't really modeling the paradigm that was intended in the modeling approach so much.
Okay, so it's a bit like also the difference to actor systems. So you can put underneath an actor system, which where the communication is via message passing. We basically raise the level of abstraction. There is no message passing happening at the programming level whatsoever.
That later part of your talk was very interesting. I thought that went further than I've seen a lot of other systems.
Yeah, thanks for a very interesting talk. So I see some similarities to active grammars, of course. Wear those glasses.
Yeah, because
But in this declarative way of programming, things get
propagate.
So in your dependency graphs, are they always acyclic, or did you think about introducing fixed point computations as an addition to it?
They are acyclic. Individual nodes can cycle. This is the fold, but there are no cycles so far between nodes. So we haven't considered yet. I've pushed all the time for the students to look at it, but we haven't done so far. So maybe attribute grammars might be a source of inspiration, you are saying, for doing so?
Possibly.
Yeah.
And the other way around.
Yeah.
In your second part of your talk, you talk about replicating the reactive program. Does it mean that in order to get conversions, the signals are limited to the CRDTs?
No, because that's what I said. What is limited to CRDTs is the implementation of the update propagation. So the update propagation algorithm and the way the graph is implemented uses CRDTs. But the user-defined computations can be arbitrary. That's what I say. Think of a reactive as being a sequence of inputs. A reactive has inputs that it depends on. Think of those inputs coming in a sequence. So it's an ordered sequence of inputs, plus a fold operator that given the current state of the sequence, it just applies the user computation, which can be arbitrary.
Your operations can still arrive in different orders at different nodes, right? So your update propagation algorithm can be all different.
Again, what can come in?
So if you have two concurrent operations and they are exchanged, they will arrive in different orders, right? At nodes.
Right, so the inputs can arrive in different orders, but then if I use a CRDT, that's where I use the CRDT to store the sequence of inputs, and then they can merge in a conflict-free way. Okay.
So I was wondering about sort of the resource requirements, memory and communication. Something you can say something about? I mean, suppose I'm interested in resource constrained systems.
Right.
I mean, this all sounds nice, but sometimes abstractions like this come at a cost. And I'm sure it's performant, which you looked at, that these other things to think about as well.
Okay, so I think there are different answers to this question. First of all, we need garbage collection here. We do have garbage collection, but this part of the work is still ongoing. So you can get memory leaks because of the nodes hanging around, and we are working on this. The other thing you said with bringing this to restricted resource devices with restricted resources, I don't think there is a conflict per se there, because given that you have so much power of knowing what depends on what, having the data flow in your hands, you can do optimizations. And in fact, we do have an implementation now, we call it Reactify, that implements not full Rescala, but a domain-specific, reactive domain-specific language for the Wi-Fi chip.
For what type?
The Wi-Fi chip of a device. You want to do computations already on the Wi-Fi chip before propagating further to the CPU and whatever. And it turns out it's a very constrained environment in terms of memory especially, and also we basically use the knowledge to locate memory in a proper way. It's not published yet, I mean, it's still work in progress.
Okay, one more question. There's some other
Happy. Very good.
Suppose you have all these components that are implemented in Rescala, and you suppose they're sort of interfaces like some kind of service interface. I guess you could do that.
Mm-hmm.
And then you want to connect them in sort of ad hoc ways. So how do you connect these? I mean, you're distributing, you're running this in a distributed way on different devices, etc. How do you connect them? Do you have some language for that?
Okay. Well, I don't know whether I get the question right, but let me try and answer and see whether I understood your classes that you have now. I'm looking at Pascal over there. So there is a Scala Loce, it's called, a version, of Rescala. It supports also other languages. Tierless reactive programming could be what you are asking for. So in this, Scala Loce was a paper last year at Uppsala also. The language supports way to specify how computations are distributed in a certain distributed architecture. So basically it gives you an integrated architecture description language, if you want, so that you can have placement of computations specified as part of your program, and in a type-safe way, in the sense of ensuring that communication cannot go wrong at runtime because of wrong placements. This is kind of on top of. You can marry this architecture description with other paradigms. Reactive communication is one of the communications that Scala Loce supports. It can be also others. It fits well together, because you have this, a distributed computation is basically a graph, and values flow through this graph. So in principle, the paradigm is very well suited for the distributed world. And then plus the architecture description language, it fits very well together. I would refer to the paper from last year. And there was a paper at eCube also about a module system for such a programming language.
Let's say that that I take a program that I've written in Rescala and I distribute it across multiple different applications or multiple different systems that are now running
No.
parts of the application. Then, if I understand your approach correctly, I will lose the transactional commitment property at the boundary between the devices.
Yeah.
Is there anything else that I lose in this process?
Let me correct you a bit. We do have, I didn't talk, I skipped it. We do have a version of the transactional semantics that is distributed. But then you have to pay a price for the coordination. Because remember, we have this structure where we keep track which transaction goes, the order of the transactions. this data structure needs to be then distributed. And we have minimized the need for coordination with some clever engineering, but still there is need for coordination. But it's there, so you can choose. That's also an important point. Since the concurrency control and fault tolerance mechanisms are hidden behind the programming abstractions, come out of the box, you can mix and match them. So if you need the strong transactional or serialization semantics, you can have it. Of course, the programmer needs to give, when someone is working on this using types for mix and matching different consistency semantics.
Otherwise, let's thank Mira again for the very inspiring talk.
Thank you very much.